hope everybody is enjoying this semester for now. So today I'm going to talk about some of my recent works on understanding the convergence of optimization algorithms for Minimax machine learning. So this is part of a project supported by the NSF scale model program. So here's the outline of this talk. So I'm going to first give a very brief introduction to what is Minimax machine learning, and then in the following 3 sections, I'm going to talk about 3 different optimization algorithms for solving Minimax machine learning problems. So we will understand the convergence properties and the convergence rates of these algorithms under different settings, and talking about their different optimality conditions. And after that, I will conclude this talk. Okay, so first of all, I'm going to give an introduction to Minimax machine learning. So in conventional machine learning, we aim to solve a minimization problem that looks like this. So here the objective, we aim to minimize an objective function over the model parameters. So in many cases in machine learning applications, the objective function takes a finite summation form, where each fi corresponds to the loss function on the ith data sample. Now this is often called a data fitting process. For example, consider an image classification application where we have an image xi and its corresponding label yi. And then we want to train a classifier h that is parameterized by the theta. So in this case, we input the image to the classifier h, and then we will receive a predicted output yi or yi hat. And then we want to measure the discrepancy between the predicted label and the underlying true label for this particular data sample. So in this case, we are going to use a loss function to measure their discrepancy. And this is defined as the ith loss, the loss function on the ith data sample. So in particular, we always use over-parameterized models such as neural networks in this classifier. And in most machine learning applications, we typically involve a large number of training data samples. And in particular, a very popular and widely used algorithm for solving the above optimization problem is the gradient descent algorithm. Well, in every iteration, we compute the negative gradient of the loss function and then use the negative gradient to update our current model parameters. So here, eta is a scalar that we call learning rate, or the step size. So the previous data fitting framework that we just talked about turns out to have many underlying issues. This is because if we do wild data fitting, typically when we use over-parameterized models, we will always concern about the overfitting issue. And in particular, in practice, we can find numerous we can train numerous over-parameterized models that can fit our training data very well. But many of them we found are lack of model quality control. For example, in image classification, we found, later on I will give a more specific example. We found that the models trained by traditional machine learning is vulnerable to adversarial attacks, in the sense that you can just slightly perturb this image, and that will completely fool the classification result of the neural network. And similar issues occurs in other domains, like in the domain invariance application. If we train the network in one data domain, it will not generalize to another data domain. And moreover, if we train a network on some population data, this machine learning model may be biased toward a particular group of people. So we have these fairness issues here. And we also have privacy issues in some other applications. So in general, as part of the next generation machine learning paradigm, we aim to perform this data fitting, and at the same time, we want to impose some desired model attributes to the machine learning model. And these model attributes can be, for example, the model should be robust to the adversarial attacks or adversarial perturbations. And very interestingly, many of all these model attributes can be imposed into the model by following the following Minimax game framework. So by solving a Minimax optimization problem, we can impose the model attributes to the model. And in the next following slides, I'm going to talk about some examples. But here is a very high-level abstract illustration. So in this Minimax optimization problem, the minimization part corresponds to the conventional data fitting part. We want to minimize the loss on the model parameters over the model parameters. And what is important here is the maximization part that serves as an adversarial game. It is used to compete with the minimization part and at the same time impose the desired model attributes. So next I'll talk about some specific applications that falls into the Minimax machine learning framework. So the first application is a very popular application called adversarial robust training. So we just, as I just mentioned, so in the standard deep learning, a deep learning classifier will, for example, it will classify this image as panda with 80% confidence. But people found that we can add very small, imperceptible small noises to perturb this image. And the resulting image, which looks almost no different from the original image. However, if you input this image to the deep learning model, it will give a completely different output with a high confidence. So this is the adversarial issue for neural networks. So it turns out that we can resolve this issue by solving an adversarial robust training problem, which is formulated as follows. So I will not go into the details into the formulation, but the high level idea is that we are still minimizing the classification loss over the model parameters. And so the minimization part is as standard as the conventional machine learning. And what is important here is the maximization part. So we introduced some adversarial data samples, CI, and we want to find these adversarial data samples by maximizing the classification loss. So in particular, if you look at these expressions, what we aim to do is to find the adversarial samples. On one hand, they should be close to the underlying true images. So this xi is the original image. We want to find these CI that are as close to these clean images as possible, and at the same time, they should maximize the classification loss as much as possible. So therefore, in summary, we have two players here. Well, on one hand is the adversarial player, which aims to find perturbed images that are close to the clean images and can also, at the same time, can fool the neural network classification result. And on the other hand, we still want to train this classification model that can perform well on these adversarial images. So if we let these two players compete with each other, and by training the model on these adversarial images, hopefully the resulting model will be more robust to these adversarial perturbations. So that is the overall idea. And the second application is called domain invariant learning. Well, in this task, we have a labeled source domain data And we want to train a classifier on this labeled source domain data. However, we would like this classifier to be applicable to the data coming from another domain, which we call the target domain. So for this target domain data, we don't have any classification labels for them. So in order to do that, we will, in this domain invariant framework, we aim to solve the following minimax optimization problem to get this domain invariant classifier. So the key idea is to obtain a feature extractor G. So this G applies to the data samples, and they generate features corresponding to these data samples. The central idea is to train these feature extractors so that they can generate domain invariant features. So for the first part is a standard classification part on the source domain. Well, we want to train this feature extractor so that they can extract good features for the classification on this source domain data. But on the other hand, we want this feature extractor to extract invariant features across these two domains. So for the second part, it corresponds to a classification across the two domains. It's a binary domain classifier. So the overall goal of this feature extractor is that, on one hand, it wants to we want it to extract invariant features across domains. Yes. Yeah, so in the first part, this exercise only comes from the source domain. And in the second part, it is a domain classification task. So this exercise can come from either the source domain or the target domain. And we will. Oh, yeah, this is supposed to be M. Yeah. Sorry for that.
Sorry, I can't hear the questions. Would you mind to repeat the questions? Thank you.
So the question is that what does this xi corresponds to in these two parts? So, and the answer is that in the first part, this is a classification on the source domain. So all the data coming from the source, all the data are labeled data coming from the source domain. And the second part is a domain classification task. Well, this data can come from either the source domain or the target domain. And this classifier F prime is a binary classifier that tries to distinguish between the source domain data and target domain data. So the goal of this feature extractor is to, on one hand, it wants to extract good features on the source domain so that the classification on the source domain data can be carried out. On the other hand, it wants to extract features that can fool the domain classifier. If that can be realized, then we can hope that this feature extractor can generate domain invariant features across these two domains. So this is where the adversarial game occurs. So we are minimizing this over G, but on one hand, one of the G is inside this classification loss, and the other G is inside the negative of the domain classification loss. So they are competing with each other. And the next example is a very popular example called generative adversarial networks. So in this task, we want to create a generator model that can generate fake images. And so specifically, we have a training set which contains a real images. For example, these handwriting digits. What we want is to train a generator so that once we input a random Gaussian noise, it will generate a fake image as similar to the training images as possible. And the way we do this is to introduce another discriminator model. And this discriminator is binary classification model that aims to distinguish between the real training images and the generated fake images. And then here we will let the generator compete with the discriminator through this minimax optimization. So on one hand, the generator aims to generate fake images, so to fool this discriminator. And on the other hand, the discriminator aims to distinguish between the fake images and real images. So if we can achieve a certain equilibrium, then we expect that the generator in the end can generate these fake images. So there are many other applications that I cannot list here. But in general, all this, we can see that in all the previous examples, we are trying to impose some features, some desired attributes to the network model. For example, adversarial robustness, domain invariance on the model by solving a general minimax optimization problem. So in the end, this motivates us to study a very fundamental problem, how to solve this minimax, a fundamental minimax optimization problem, where we are minimizing this bivariate function over part of the variable x, and at the same time we are maximizing this function over the other part of the variable y. And what is special here is that in the previous applications, usually because we use a lot of neural networks, so usually part of the model is non-convex. For example, if you fix the other part, now you fix the other variable y, this function is non-convex. And if we fix x and consider the other part, now this function in some applications it can be concave or strongly concave, while in other applications it can be generally non-concave. So this is very different from classical saddle point problems where this bivariate function is convex in x and concave in y. So here we do not have this nice global geometry of the function. So the two key research problems that we aim to answer is that, first of all, for this general possibly non-convex and non-concave minimax problem, how do we define this optimization goal? What is the proper optimization goal of this problem? And the other question is, how do we design computation efficient and provably convergent algorithms for solving these problems? And in particular, we want to understand how fast do they converge in different scenarios. So in the first part, I'm going to talk about a very classic and simple algorithm called gradient-descent-ascent algorithm. So let's consider this generic minimax optimization problem. And since we are minimizing over x and maximizing over y, so very, very intuitively, we may want to try gradient descent on x and then try gradient ascent on y. And that is the key idea of this gradient descent-ascent algorithm. Basically, to update x, because we are minimizing over x, so we do gradient descent on x. So specifically here, we only compute the partial gradient with regard to the first variable, which is x. So we basically do gradient descent on x. And then we switch to y and do gradient ascent on y, where we use the partial gradient with regard to the second variable. And there has been a lot of existing studies on the convergence properties of this algorithm. Let me see if I can put this. Okay, it doesn't work. Never mind. So for example, the convergence of this algorithm has been studied under some global function geometries. For example, for convex concave problems or bilinear problems. Well, the bilinear problem means that if you fix x, the function is linear in y and vice versa. And also for the functions that satisfy the so-called Poyar-Civics geometry, which is pretty similar to the strong convexity. So under this global function geometries, it has been shown that this GDA algorithm, very simple algorithm, converges, its function value converges to the optimal value. And moreover, under even stronger conditions, like convex, strongly concave conditions, or even strongly convex and strongly concave conditions, we can establish the convergence of the model parameters. So, however, all these conditions are global geometries that are not necessarily satisfied in the non-convex minimax machine learning. And recently there has been some studies that establishes the convergence of this algorithm on the non-convex geometries. So the convergence has been proved under either the non-convex concave geometry or the non-convex strongly concave geometry. And what they show is that a certain notion of gradient converges to 0 at a sublinear rate. And this result is equivalent to say that the algorithm is asymptotically stable in this sense. So the increment asymptotically goes to 0. However, these convergence results are relatively weak in the sense that they do not imply the convergence of the model parameters. And moreover, there's another question in the non-convex scenario. That is that we are not clear. It is not clear how does the local non-convex geometries affect the convergence of this algorithm. So in the first work, we study a slightly more generalized version of the minimax problem. Well, we in addition to the basic minimax optimization problem, we consider two regularizers. One regularizer G applies to the X part, and the other regularizer H applies to the Y part. And for this problem, we can understand this as follows. So first of all, we can introduce because we have a inner maximization operation and an outer minimization operation. So we can define this, we can define the inner maximization part as a function. So we can introduce, we call this function the envelope function. It's just an envelope over the Y. So in particular, this function is defined as follows. Fix any X. Now we consider, now X is here, is fixed. Then we consider the maximum value of this function. So we can define this function. Now, once we define this function, the maximization part in this minimax optimization can be absorbed. And then we can equivalently write this minimax optimization into the following minimization part. Okay. They are equivalent because the maximization part is hidden inside the phi function. So this is just a rewrite of the reformulation of the problem. So here are some very standard assumptions. Basically, I just want to highlight that first of all, this objective function is differentiable. We assume it's differentiable, and it is non-convex in X, but it is strongly concave in Y. And then the other assumption we impose is on the regularizers. Well, for the H part, we assume it's a convex regularizer. Well, for the G part, it could be any general non-convex regularizer. Okay, so let's look at this reformulation. So we just rewrite that minimax problem into this minimization problem. Well, the maximization part is hidden inside this phi function. So this is just a rewrite reformulation. Now, under the previous assumptions, we know that this this maximization problem is strongly concave because we assume y is strong, f is strongly concave in y. Therefore, it has a unique minimizer. So this problem has a unique minimizer, and then we denote the unique minimizer as the y star. And because the problem depends on x, so this minimizer is also a function of x in general. So we will define this y star x mapping, which is very useful as we develop the algorithm later on. So some propositions here, we can show that this this maximizer mapping is continuous, Lipschitz continuous in X. And also, we under this condition, with this result, we can further derive that this envelope function phi is actually a differentiable function. And in particular, the gradient is given by this formula. It is partial derivative with regard to the first variable. And then for the second variable, we will insert the corresponding maximizer y star x. So we usually call this y star x as the best response to the variable x, right? Because it is defined as the best response in this way. It is the maximizer of this problem. And since we just rewrite this minimax problem into this minimization problem, so we can just define the optimization goal as the goal of the classic minimization, non-convex minimization. So here we define the optimization goal as to find a critical point of this minimization problem, which means that at this critical point, the subdifferential must contain 0. So here, subdifferential is a generalized notion of the normal gradient. So this is called the first order optimality condition. And then to solve this regularized minimax problem, we developed the following proximal gradient-descent-ascent algorithm. Which basically takes, in addition to the gradient descent and gradient ascent part, we further do 2 proximal mappings to handle the regularization part. So intuitively, for example, if these regularizers are constraint sets, then these proximal operators will simply become projection operators. So to understand this algorithm, the convergence of this algorithm, we take a very different perspective. So before we talk about the convergence of this algorithm, let's talk about the convergence, the analysis of classical minimization algorithms. So in the classical machine learning, when we talk about minimization problems, for example, if we apply gradient descent to solve this problem, then here's a visualization of the optimization process. This is the landscape of the object function. And we start from here and then following gradient descent, we are going down and to some local converge to some local minimum points. So in this visualization, the negative gradient is kind of serves as the gravity force that drives the model down to the landscape where the energy is lower. So physically, we know that as this point goes lower, the gravity potential will decrease. And actually, we can show that for this minimization, for many minimization algorithms, they do have an implicit potential function that decreases along the optimization path. Yeah, it may or may not be the function value depending on the specific algorithm. Yeah, and in the following 2 slides, here's one slide and this is another slide. I just listed 4 different classic minimization algorithms. They are developed for solving different classes of minimization problems. They look somewhat different, but what is, so for example, we have this proximal point algorithm for solving non-smooth minimization. Gradient descent, this is a very well-known algorithm for solving differentiable minimization problems. Proximal gradient for solving composite minimization problems, and cubic regularization for solving higher order minimization problems. All these algorithms are developed to solve different classes of problems, but in their convergence analysis, they share a common property. That is, we can always establish an implicit potential function and show that this potential function monotonically decreases along the optimization paths. Now, for example, for these three algorithms, as well as the cubic regularization algorithm, the potential function is simply the objective function. And for some momentum accelerated gradient method, the potential function looks a little bit different. But the key message is that for the classic minimization algorithms, we always find this potential decrease property first, and then leverage this potential decrease to prove the convergence result. So with this potential decrease property, we can show all the convergence results can be naturally derived. For example, we can show that these algorithms are asymptotically stable, and eventually they will converge to some stationary or critical points. Okay, the P, it depends on the algorithm that we are looking at. For example, for this gradient-based methods, the P equals to 2, this exponent. And for the higher order cubic method, the P equals to 3, because we are going to a higher order, we are leveraging higher order information, so the decrease will be bigger. It has a faster convergence. Okay. So therefore, to summarize, in the classic minimization algorithms, for classic minimization algorithms, we prove their convergence following this roadmap. We find a potential function, prove that it is monotonically decreasing, and then do the rest of the job. Now, let's go back to this Minimax optimization problem. Okay. Now, first of all, because we are dealing with mean and max here. And in particular, in the algorithm, we are doing gradient descent, and gradient ascent. So apparently the objective function, if we look at this objective function, its value will be oscillating because we are doing alternations between a descent step and ascent step. So this is not so it is not clear if we can find a similar potential function for these minimax problems. And however, under standard conditions, we do find that even for these minimax problems, we can still identify an implicit potential function, which takes the following form, as shown in the blue equation. So this hxy is the potential function corresponding to this proximal GDA algorithm. I will talk about this later, but essentially what we show is that understand some choices of learning rates, this function is monotonically decreasing over the iterations. So all these terms, they are strictly negative. So it is strictly monotonically decreasing. And if you look at this, the form of this potential function, it is closely connected to this minimization problem. So first of all, it contains the objective function of the minimax problem. So remember that this phi plus g, it is basically equivalent to the minimax objective function. So it is this objective function regularized by a periodic term. So for this part, it keeps track of the optimization progress in X, and for the other part, for this quadratic part, it tracks the optimization progress in Y, because in general, in the end, we expect Y to converge to the best response to X. So in particular, suppose xt goes to an optimal point X star, and yt goes to the corresponding optimal best response point, which is the maximizer associated with X star. Then we can see that because y goes to y star, so this term diminishes to 0. So then the value of the potential function will converge to the value of this to the desired optimal value of this minimax problem. So this shows that this potential function is closely connected to the minimax problem. And then once we have that potential decrease property, we can establish all these useful properties of the algorithm. We can show that all these model parameters, they are asymptotically stable. And in particular, the YT sequence will converge asymptotically to the best response point, Y star. So Y star of XT. Okay. Yeah. So the question is, what is the assumption with regard to the function f in X? So here we just assume it is general differentiable and non-convex function. Yeah. So there's nothing with it. Right. And this property does not imply any convergence of these sequences. So in the next result, we can, by further leveraging this the previous asymptotic stable properties, we can prove that every limit point of this sequence converges to a critical point of the of this minimax objective function phi plus g. So and this result only shows the convergence of this algorithm and does not show the convergence rate of the algorithm. So in the next part, I think I'm going to skip this a little bit. So in the next part, we are going to talk about the local convergence properties of this algorithm by leveraging some local non-convex geometries. And the geometry here that we're looking at is this local or civic type geometry. Which basically says that if we look around a neighborhood, so within a neighborhood of a certain critical point, the function satisfies this growth condition. So the function value gap is bounded by the gradient to the power of certain parameters, and this parameter theta controls the geometry of this function locally. And intuitively, what it says is that, for example, if a theta is small, then locally the function looks very flat, and we expect the convergence to be slow. And otherwise, if the theta is large, then the function looks sharp, and we expect the algorithm to converge much faster in this case. So, sorry. Nearby is meaning that so this nearby means that within a small neighborhood of that critical point. So in terms of L2 distance. Yes. So you can always find a sufficiently small neighborhood where this holds. Yeah. So in general, the non-convex functions do not satisfy global geometries. So we can look at the local geometries instead. And we can, under this geometry, we can show a strengthened result where this algorithm has a unique limit point. So all the sequence, so the sequence, parameter sequence converge to a single unique limit point, which is also a critical point of this minimax problem. And moreover, in different regions of the geometry parameters, we can establish different types of local convergence of the algorithm. So basically, if the local geometry is flat, the convergence is relatively slow with a sublinear convergence. If the theta is relatively large, the algorithm can converge at a superlinear rate. And in the second part, I'm going to briefly talk about a simple extension of this algorithm.
Could I ask a question? Last slide. Sorry. How do you estimate theta for the local geometry, or this is just assumption?
That's a great question. So this is so what happens here is that we can show that for a wide class of functions, this theta exists, and it is between 0 and 1. But the specific value really depends on the specific problem that we are looking at. Yeah, so that's why here it is more like an assumption, like if the function falls into this local type of geometry, then the algorithm has this type of convergence.
But is there a way to kind of quickly probe the landscape and estimate theta, or there's no way of doing that?
There are many works working on that, and it turns out that working out the specific value of theta for a particular function is in general highly non-trivial if we consider slightly complex problems. So okay. I would say this is maybe we can use some numerical methods to estimate. So I mean, by looking at the type of convergence of the algorithm, we can go back and maybe estimate the value of theta.
Okay, so it's more like a chicken and egg problem now.
Yeah, exactly.
Okay. All right, thanks.
Yeah, in general, this is not an easy problem.
Okay, thanks.
Yeah, so next I'm going to talk about simple idea that how to accelerate this algorithm with momentum. Because we are talking about gradient methods here. So a very classical idea is that we know that for classical gradient descent methods, they can be accelerated by leveraging momentum. So what is momentum here? So the idea is to apply these momentum schemes to accelerate this minimax optimization algorithm. And I will directly go to the algorithm part. So it's basically, in addition to in these two standard gradient steps, we introduce two extrapolation steps. So before we do the gradient step, we extrapolate the current point using the past history information. So these two extrapolation steps, they introduce almost no computation cost because they are simple extrapolation. And in particular, for these two momentum schemes are slightly different in the sense that here in the final update, we use y tilde t in these two locations. But in the second update, we only use the extrapolated point at one location. So this is because when in the x step, we are minimizing this non-convex function fx plus gx. So therefore, we want to apply the heavy ball momentum, which is designed for non-convex functions. And in the y step, because it is a strongly concave function, so we want to apply a popular Nestrov's momentum in this one. And this is the difference. And we can show that, again, we follow the potential function idea. We can show that for this algorithm, it also has an implicit potential function. That takes a more complicated form, and compare with the potential function of the vanilla proximal GDA algorithm, it has this additional term. And this additional quadratic term is induced by the momentum effect of the algorithm. But in the end, we can show that this potential function, monotonically decreases. And then we can establish all similar types of convergence results of this algorithm. So in particular, we can show that with this potential function, this algorithm is allowed to use a larger learning rate. And this will further improve the iteration complexity of this algorithm for achieving an epsilon accurate stationary point. So you can see that by comparing the complexity of this algorithm with the proximal GDA, so this one does not have momentum, and the bottom one, this small m, stands for momentum. So comparing their complexities, you can see that with momentum, it has a better dependence on the condition number. So this kappa denotes a condition number which is strictly greater than 1. Yes. So we're looking at the non-convex in X and the strongly concave in Y. Yeah. Yes. So this is for the standard GDA algorithm. It depends on the condition number to the power of 6. Yeah. And with momentum acceleration, the dependence on the condition number can be substantially improved. And we have some experiments on the adversarial training to demonstrate the efficiency of this algorithm. So basically, the red curve corresponds to our momentum accelerated algorithm, and the other 3 curves correspond to comparable single loop algorithms. Some of them, they do not have momentum acceleration, and the algorithm may look a little bit different in general. So, but in general, we can see that with momentum acceleration, our algorithm converges the fastest. So, for this figure, the Y label is the training loss, and for the right figure, the Y label corresponds to the test accuracy. Okay, and I'm going to spend the rest 10 minutes to talk about the third algorithm, which is developed to find local minimax points via the cubic regularization technique. So going back to this very standard minimax problem, so remember that we introduced this envelope phi function so that we can rewrite this minimax problem into this minimization problem. And we can, in the existing literature, we defined, it has been defined this global minimax point. So in this definition, X star, Y star is called a global minimax point if X star is a minimizer of this phi function, and at the same time, Y star is the best response to X star, in the sense that Y star maximizes this function with X star being fixed. So this is the definition of this global minimax point. And it has been shown that if F is a continuous function, then such a global minimax point can always exist, no matter the function is non-convex or non-concave. But in general, finding such a global minimax point is NP hard, because we know that finding a global minimum in non-convex optimization is already NP hard. So the idea here is to consider relaxing this global minimax condition. So instead of global minimax, we can consider this surrogate definition, which is called the local minimax point. So X star, Y star is called a local minimax point so basically everything in the definition of global minimax is localized. For example, now X star is only requires to be a local minimizer of this phi function. And even for the phi function, it is locally defined within a neighborhood of this Y star. And at the same time, Y star is only required to be a local maximizer. It's a local best response to this function fx star. So basically everything is localized. And turns out that for this local minimax point, we have sufficient and necessary conditions characterizing this local minimax point. By comparing these two conditions, what is important is that, so first of all, it must satisfy the first order stationary condition. The gradient at this point must be 0. This is very intuitive. And what is important here is the second order conditions. In both the necessary and the sufficient conditions, we require that at the local minimax point, so first of all, the Hessian matrix at y must be a negative definite. This is because y star is required to be a local maximizer. So this has to be negative definite. And then for the x part, we require this very complicated matrix to be positive semi-definite or positive definite in the sufficient condition. So basically, these are the equivalent characterizations of the local minimax point. And the property is that if the function is non-convex and strongly concave, then we can say that global minimax point can be guaranteed to be a local minimax point. Now, it's a little bit tricky here is because in general, for minimax problems, global minimax may not necessarily imply local minimax. So even though this is a localized definition of global minimax, but they could be very, very different. So the local minimax is not a subset. It is not necessarily a subset of global minimax. So that is the counterintuitive part. But under this strongly convex, non-convex, strongly concave conditions, global minimax is guaranteed to be local minimax.
Could I ask a quick question? Why is this the case? Why does, well, I guess when you talk about local minimax, it's still locally minimal and locally maximal, right?
Yes, but since everything is localized, I guess here we can construct a very, that's why it's counterintuitive, because if you look at the counterexample, it is not, I think that the tricky here seems that the f can be non-convex and non-concave. So the function class of f is a very large class. And for this class of functions, we can generate very, very weird functions, such so that their global minimax. In fact, it can be shown that global minimax may not even necessarily be a stationary point. So this means this minimax optimization problems are fundamentally different from the classical minimization problems.
Okay, thanks.
Yeah, I know that is. They are not complicated. It's just like a two-dimensional example. Yeah, I don't have that example here, but I can definitely send out the reference. But the idea is, but it is surprising that with such a very simple example, these two definitions are may not necessarily a subset of each other. Yeah, so they only have a small overlapping subset.
Oh, I guess correct me if I'm wrong. When you constrain your local minimax point, it might locate in the boundary of the local neighborhood you're constraining, which may be like regular points of the function, not stationary points at all. But then the global minimax, well, actually, your statement is actually global minimax. It's not stationary.
Yeah, may not be stationary. Yes.
I see. Okay, maybe we'll delay it until end of your talk.
Okay. Yeah. So here is a little bit counterintuitive, and for many machine learning problems like the GANs and adversarial training problems, some papers show that under some conditions, their stationary points corresponds to local minimax points. So the key question here is that can we develop an algorithm that globally converge to local minimax points of in this minimax optimization? And these are the conditions that needs to be satisfied in order to be local minimax. So it's first order stationary condition, and the second line is the second order conditions. So the one sentence to summarize the existing work is that the existing work proposes 9 different second order algorithms for finding the local minimax points, but all of them only have local convergence. So they require to be initialized sufficiently close to these local minimax points, just like the Newton's method, in order to locally converge to these points. Here we are looking at a globally convergent algorithm. So the intuition is to observe that these second order conditions has close connections to the Hessian matrix of the envelope function phi. We can show that for non-convex strongly concave problems, the Hessian matrix of phi is characterized by the following G matrix, and so this is the formula for this G mapping, and we can see that this G mapping is almost identical. It is exactly the same as the green part in the second order condition. So therefore, to satisfy this green part, we just require the Hessian of this phi matrix to be positive semi-definite. And for the other second order condition, it is automatically guaranteed because f is strongly concave in Y. So this Hessian has to be negative definite. So in summary, this green condition, this complicated green condition, turns out to be a very simple condition, which means the Hessian of these phi functions is positive semi-definite. And therefore, we can summarize. So those set of second orders, those set of conditions of local minimax points are equivalent to these two simple conditions. So the first order stationary condition can be shown to be equivalent to this condition. So to be equivalent to the first order stationary condition of the phi function. And then the other second order conditions are equivalent to this condition. And surprisingly, this falls into the classical minimization, non-convex minimization problem. Well, this is basically called a second order stationary point of the function phi. So, and we have a classical, well-known classical algorithm for finding such second order stationary points. And that is the cubic regularization algorithm, which is written below. So in order to find a point that satisfies these two conditions, this cubic regularization update is proven to converge to those second order stationary points. But so the question is, can we apply this algorithm directly here to find these points? And the answer is no. This is because in order to implement this algorithm, we need to compute the gradient and Hessian of this phi function, which actually, because phi is defined in a maximum form, so their gradient and Hessian are implicit. And these are the analytic formulas for the gradient and Hessian. So to compute this gradient and Hessian, we need to know the best response of Y to the current X. Therefore, we need to first develop another algorithm to compute these two gradients and Hessians, and then we can go back to utilize this cubic regularization method. So this motivates the development of this cubic GDA algorithm. Well, the general idea is basically first we run multiple steps of gradient ascent to estimate, to get an approximation of the maximizer Y star. Once we have this approximated maximizer, then we can plug them into this formula to replace Y star by their approximations. And then we can construct an approximated gradient and Hessian. And once we have this approximated gradient and Hessian, we can use them in this cubic regularization update. So you can see that we further substitute this approximated maximizer into this cubic regularization update. And this is the overall algorithm of the cubic GDA. And under standard Lipschitz, these assumptions are quite standard, similar to the assumptions that we introduced before. We can show that both the gradient and Hessian of this phi function are Lipschitz continuous. And further, interestingly, we can still identify an implicit potential function for this cubic GDA algorithm. So the potential function looks like this. It is again the objective function phi regularized by some quadratic terms and cubic terms. So this is due to the cubic regularization. And we can show that this function is monotonically decreasing along the iterations, over the iterations. So in particular, we can show that every limit point of this algorithm is a second order stationary point of the phi function. And we just showed that this is equivalent to being a local minimax point. So in the end, we can further prove a convergence rate of this algorithm. Well, the convergence criterion, the convergence criterion is the norm of the gradient and the negative, the smallest eigenvalue of the corresponding Hessian matrix. So these two criterions are to measure the optimality of these two conditions. So we can show that this convergence criterion converges at a sublinear convergence rate. And so I will give a very quick conclusion of this talk. So basically, we have we showed that the three minimax optimization algorithms that we talk about, they all admit an intrinsic potential function, which can be leveraged to prove and understand the global convergence properties of this function. So this might be a very interesting perspective to unify the different optimization frameworks. And as a future study, we are now looking at the cubic GDA algorithm for non-convex concave problems, and also develop stochastic variance of these algorithms. Yes, thank you very much. And I will take questions.
So I just want to follow up on that question, that how do I have an intuitive understanding of the statement that the global minimax thing is not stationary? What is sort of like a mental picture I can have? This is with respect to the local and global thing.
Yeah.
Right? Because I would always imagine, when you say not stationary, I mean, is a global minimax points going to be a global minimum?
No. So if you look at here, that so the global minimax point means that the x is a minimum for this phi function, and y is a maximum for the f function. So but the stationary condition is defined as the gradient of f. The gradient of f is 0 at this x star and y star point, right? But X star only minimizes this phi function, not the F function. So I think this is the difference here. So basically the definition of stationary point is in terms of F, not in terms of phi. So that's why
I see. Okay.
we may have a counterexample. Yeah.
So I guess what's happened is that the X star is a global minimal for phi, but not necessarily guaranteed to be a global minimal for F.
Yes, exactly.
Extra term.
Yeah, right. Because you have the other variable y there.
I see. Okay, so yeah, because the definition is with respect to F, not with respect to your envelope function.
Yes, exactly.
Okay, and then I guess is that the same thing with respect to the local version? Because in your local version, you have this constraint of epsilon 0, right? So like a local neighborhood, I guess that's the same thing. Is that because of this local constraint, whatever you are doing, which is now phi epsilon, it's definitely behaving very stringently compared to like the global.
Yes, these two can be very different in general.
Okay.
Yeah, depending on the value of the epsilon.
Okay, cool. Thank you.
Yeah, thanks a lot. Thanks for asking the question. Great question. Yeah, I can show three comments in the chat box. Okay, okay. Mm-hmm. Okay. Okay. Yeah. I want to thank everyone for joining the seminar today. It's a great pleasure to see everyone here. Yeah, and hopefully we have more people show up at the semester. Maybe we can have some cookies here to attract people. Actually, there is a plan to have cookies and coffee. Okay. Because of the current state of the pandemic, we didn't want people to eat and so on. Yeah. Without their home. So, yeah, that's right. But yeah, typically we have pizza for this. Hopefully we got a few. Okay. Yeah, thanks everyone again for joining the seminar. Yeah, thank you. Thank you.